Today I'll be talking about the Otto cycle. So in the Otto cycle, states 1 to 2 will be isentropic compression, 2 to 3 will be heat in, 3 to 4 isentropic expansion, and 4 to 1 is heat out. Today we'll be doing a hot calculation, which if you see this in a question, they might say like variable specific heat. And we'll be calculating the thermal efficiency. So at state 1, we're given pressure at 100 kPa, temperature is going to be 315 Kelvin, and at state 3, we're given the temperature at 2050 Kelvin. We're also given the compression ratio of 9 and the working fluid as air. So to begin, at temperature 1, which is 315 Kelvin, we can see that the VR1 value is going to be 549.8. I like to keep everything in a table just because it helps to keep track of all your numbers. And we're also going to be finding the U1 value. So something important to note is that for the Otto cycle, these are generally closed cycles or closed processes. So you're going to be mainly looking at the U value. There are other cycles that require you to find the enthalpy. Some require enthalpy and internal energy. But for the Otto cycle, more often than not, you're probably going to be mainly looking for the U values to solve your calculations. So we found U1 to be 224.85 kilojoules per kilogram. And as you can see, we have nothing for state 2. So how do we relate that? How do we find our numbers for that? Well, we're given our compression ratio. And we know that our compression ratio is equal to the specific volume of state 1 divided by the specific volume of state 2. This can also be related by VR1 over VR2. So we need to find VR2. So let's rearrange. And we can see that VR2 is going to be equal to VR1 divided by our compression ratio. So we can solve for VR2 and see that VR2 will be equal to 549.8 divided by 9, in which we will get 61.09. I'm rounding for that number. And I'll just put that up here in my table. So then using our VR2 value, we can interpolate using the thermodynamic tables, and we can find our U2 value. So I'll do 61.09 minus 59.32 divided by 62.13 minus 59.32. So basically for these numbers, I found on the tables, whatever tables you're using, if we take our VR value and we look on the tables, for my VR value, there was no specific matching VR value. So I found where it was in between. So I found 59.32 and 62.13. So that's where it fell in between. So that's why I set up my interpolation the way I did. And I'll set this equal to U2 because that's what I'm going to be looking for. And I'll use the corresponding U values to each of these. So U2 we're trying to find for 61.09. I'm going to subtract 544.02, which is the corresponding U value to our 59.32 VR value, all divided by 536.07, which is the U value for this corresponding VR value, minus 544.02. So then we can solve for U2 to be 539.649 kilojoules per kilogram. Again, just adding that up here to my table. And we actually were given a temperature for state 3. So we can go straight to the table for that. We see that T3 at 2050 Kelvin. Our VR3 value can be seen to be 2.555, and our U3 value to be 1726.8 kilojoules per kilogram. Again, just adding these to my table. I highly recommend making a table just because it really helps throughout the whole process. Usually these cycles require a lot of calculations, so knowing where all your numbers are can be super helpful for that. Alright, and so as we can see, we have nothing for state 4 now. We do need to find this U value, so if we look at our PV diagram, we know that our compression ratio is equal to the specific volume at state 1 divided by the specific volume at state 2. Well, we can also see that V4 and V1 are equal, or constant, you could say, and 2 and 3 has a constant specific volume as well. So our relation of the compression ratio from 1 to 2 would also be equal to the compression ratio from 4 to 3. So seeing that in calculation, we can write that down. It's going to be VR4 divided by VR3 is also equal to the same compression ratio. Solving for VR4, we get that VR4 is equal to our compression ratio times VR3. And solving for VR4, we can get that it's equal to 9 times 2.555. We get a VR4 value of 22.995. And using that, we can interpolate again for our U4 value. Minus 21.14 divided by 23.29 minus 21.14 is equal to U4 minus 810.62 divided by 793.36 minus 810.62. Again, picking the VR values that my VR value that I found falls between. This U value corresponding to this VR value, this U value corresponding to that VR value. In doing so, we can solve for U4, which we find to be 795.728 kilojoules per kilogram. So we have U4. Alright, so now that we have all of our U values, I could have solved for like the temperatures, but all we really need for this calculation is the U values. So our thermal efficiency can be calculated through W net divided by our heat in. And W net is also equal to our heat in minus our heat out. So you can also do it work in minus work out, but today I'm going to do heat in minus heat out. Our heat in can be seen on the table between states 3 and 2. I want the change in the U value, so I'm going to do 3 minus 2 for that. So U3 minus U2, we're going to get 1726.8 kilojoules per kilogram minus 539.649 kilojoules per kilogram, which will equal 1187.151 kilojoules per kilogram. And solving for Q out Q out is between state 4 and state 1. So since I want the change in U, I'm going to do U1 minus U4, where we'll get 224.85 kilojoules per kilogram minus 795.728 kilojoules per kilogram, which will equal 570.878 kilojoules per kilogram. Keep in mind the sign convention. Here it works out. Our Q in is positive and our Q out is negative, which follows the general sign convention for those energy transfers. But just keep that in mind when you're doing these calculations to watch out and make sure that your signs line up with the direction that this transfer is occurring. So we can calculate our W net to be 1187.151 kilojoules per kilogram minus 570.878 kilojoules per kilogram, And we can see that our W net is going to be equal to 616.273 kilojoules per kilogram. And now we can find our thermal efficiency. So again, like we said, thermal efficiency is equal to W net divided by Qn. So we can do 616.273 kilojoules per kilogram divided by 1187.151 kilojoules per kilogram. And once we do that, we can see that it equals 0.5191, which if we multiply that by 100 to get it in percent form, is 51.91% for our thermal efficiency. So I hope this was helpful.